So welcome everyone to our ilifu online training workshop. Thank you very much for joining us today. We'll be presenting the first of 4 sessions today, which will provide an introduction to ilifu, and then we'll follow this with 3 more sessions over the next few weeks, every Tuesday until the 23rd of September. And the following sessions will expand on the introduction and cover other more advanced topics. I wanted to start by introducing the ilifu support team. Walter Salima is our astronomy support specialist. Walter, you're welcome to put your camera on, and yeah, thank you. And Dane Kennedy is our bioinformatics support specialist. And Tinas Klutter, who unfortunately is not able to join us today, but he's our systems administrator and also provides support to users. And myself, I'm Jeremy. I'm the ilifu operations manager. So please note that the training sessions are being recorded. We'll make these recordings along with the presentation slides available from the ilifu website as a resource for everyone to use. And we also go through a few demos during the presentations, and these are available in a GitHub repo as tutorials, and we'll post the link for that in the Zoom chat. Otherwise, the link can also be found in the slides later in the presentation. So the topics for today will be an introduction to the ilifu facility and its primary services. We'll go through the cluster's directory structure and talk about the available software environments and introduce the main 2 services that most users are interested in using, and that includes Jupyter and the ilifu Slurm cluster. And Dane will be presenting on the introduction to Slurm section today. So there's quite a lot of material to cover. So we're going to go through the presentations and talk about the content, and then we'll host a Q&A session at the end of the workshop where we can address any questions that you might have. You're welcome to post questions during the workshop in the Zoom chat, and the support team can address them at the time in the chat. But otherwise, we can also respond to any questions during the Q&A at the end. So before we start, I just want to point out the available support channels and where to find information about ilifu services and where to get help. You can email the support team at support.ilifu.ac.za. We have a ticketing system and a team of support personnel who will respond to questions or issues that you might be having. Our user documentation is available at docs.ilifu.ac.za. So I'm just going to flash this up for everyone's information. So the user documentation includes a step-by-step guide under the Getting Started section, from applying to access, dealing with SSH keys, and how to log into different services, and how to submit your first job. And then some of these topics are expanded on further in the technical documentation section. And there's also domain-specific information such as for astronomy, bioinformatics, as well as other information like data transfers, data management under this section. We do update our user documentation with new information about new services or system changes. So please, we invite you to make use of the documentation and check this documentation. Perhaps you can resolve an issue through this before contacting us. And then we also have an ilifu status page. It's available at status.ilifu.ac.za. Also just going to flash that up. So here's the status page. It provides a current state of the ilifu services. So at the top of the page is just a general overall status. And then there are different sections of the ilifu cloud environment available. So from the Slurm cluster, different infrastructure components and other components like the web-based services and Jupyter. So this is really useful if you're experiencing an issue to come and check here, see if there's an outage reported or if some services are out of operation. And if we're doing maintenance or there are ongoing issues, we'll post incidents at the bottom of or the incident post can be found at the bottom of this page. And then, as I mentioned, these videos are recorded and we put them online on the website, on the ilifu website. So if you go to the ilifu website, there's a section for training, and latest training will have the latest videos. So we'll post these videos as soon as possible, but you can find March's videos with the same content already available. So before we get into ilifu, I just wanted to cover a few concepts related to high performance computing. Just a bit of background. So when we talk about high performance computing, or HPC, we're talking about combining a bunch of computers or compute servers over a high-speed network for greater processing power and speed to solve complex problems. And these are typically problems that you wouldn't be able to solve with an ordinary or even high-end desktop or single workstation. Another reason you might want access to an HPC environment is to access large data that could not be stored on a personal workstation just on account of the data size. So these are the two main reasons to make use of a HPC environment. And we often refer to a server as a node, a compute server, and a collection of nodes in a pool we would call a cluster. And in our case, we often refer to the ilifu Slurm cluster. So that's the main workhorse that we offer. So ilifu is a cloud-based facility for data-intensive research in the fields of astronomy and bioinformatics. We provide users remote access to high-performance computing resources, storage, and other services that support a range of projects and requirements. We use open source cloud software, OpenStack and Ceph to manage storage. And these tools allow us to manage a flexible environment, including the ilifu cluster and other services that we'll talk about. There's also a large focus on data management, both for storage and transfer, given the amount of data associated with many of the projects that we support. The two main methods of interacting with the ilifu services is either via a command line interface using a shell terminal, or through web applications accessed using a browser. If you want to submit jobs to the large pool of resources in the Slurm cluster, you'll want to use the terminal interface. To connect remotely to ilifu via terminal, we use SSH, or secure shell, and authentication is managed using SSH keys, which I'll touch on shortly. So on the left is an example of what terminal access would look like. And the command below the picture is how one would SSH to from your local workstation to the Slurm login node, or for example, a transfer node, which is dedicated for transfer activities. So it would be SSH and your username at slurm.ilifu.ac.za, or SSH and your username at transfer.ilifu.ac.za. So once you've SSH to ilifu, you can run typical Linux commands to navigate the file system, browse directories that you might have access to, edit files, and submit jobs to the cluster from the Slurm login node. On the right of the slide, I just have a screenshot of the application dashboard that is part of the IDEA Science Gateway, which is a portal for accessing all the web-based applications that we host using a web browser. So these are the two main ways of interacting with our services, either via terminal or by a web application. So the IDEA Science Gateway makes use of single sign-on, or SSO, single sign-on. This essentially allows a user to sign in once into the application dashboard, and then from where you can access a number of different web applications, including Jupyter, Carter, Globus for transfers, and SSH key management tool, and other useful sites or tools. And the key here is that you're able to access these tools without having to log into the individual services. So that's where the single sign-on comes in. And you just have to sign in once. And I'll demonstrate this when I demonstrate Jupyter later on in the session. And note that all the web-based applications can also be accessed directly from their respective URLs. So just at the bottom right here, as an example, so you can access Jupyter or Carter through these URLs from the web browser or from the application dashboard. So just a brief note on SSH keys, most people don't have to deal with SSH keys until you need to use an HPC or another remote environment. So this can be a bit of an initial stumbling block for some users. In order to access the terminal environment, you need to use an SSH key authentication. So an SSH key is an authentication method that grants you access to a secure shell connection between your machine and a remote machine, in this case, ilifu. So it allows you to interact with the cluster over the internet. So you'll need an SSH key on the particular workstation or computer you're using to access ilifu. And these keys need to be associated with your ilifu account. So when you create an SSH keys, you create a pair, and it creates a private key and a public key. And you provide us with your public key on signup. Please never share your private key, because that can be a big security risk. And then when you access ilifu over SSH, your private key on your local workstation is compared to the public key associated with your ilifu account. And if they match, you'll be granted access. So if you haven't generated an SSH key on your computer before, you will need to do that in order to use the ilifu cluster. Another reason to generate a new SSH key would be if you got a new computer, or if you want to access ilifu from an alternative computer, or perhaps you formatted your laptop and you've lost your SSH key. These are all reasons to generate a new SSH key. So each computer requires a unique SSH key so that our system knows which computers to allow to connect to it. There's very good information on this GitHub link on the slide of how to generate SSH keys for different operating systems. And this link is also available from our user documentation in a section on SSH. Included in the IDEA Science Gateway application dashboard is a link to an SSH management tool. So users are able to manage their own SSH keys that are associated with their ilifu account. So you can add or remove keys from your ilifu account when necessary. And it is also accessible from this link at the bottom of the slides, also available in our user documentation. So I've included this slide just to show an example of SSHing to the Slurm login node and running some typical Linux commands. So starting from the top, from your local workstation, using a terminal application, you'll run the command SSH followed by your username and then @slurm.ilifu.ac.za. And then if successful, you'll be presented with a welcome message. But you'll also see that the command line prefix will change to indicate that you're now on the Slurm login node. So that's the head node in the Slurm cluster. And you can now run commands within the shell environment on the ilifu cluster. You can show your current path using the pwd command, print working directory. And you can also list the contents of your working directory with ls. You'll see a link to your workspace directory here called workspace, and new users will see a README file that has helpful information. And then finally, the last example on the slide is just listing the contents of the /idea/projects directory. And you can see here a number of astronomy projects. This is where the astronomy projects exist on the cluster. Right, so on that note, and given there's a lot of data moving through the cluster, we like to place emphasis on the correct use of designated storage spaces or directories for us to best economize disk space, but it's also that storage usage is properly accounted for against supported projects. So this brings us to the directory structure we use on ilifu. So all users have access to common folders. Each user will have a directory in /users, also known as the home directory. And every user will also have a folder on the Scratch mount. So we currently have Scratch3. So you will have a user directory in /Scratch3/users. So the user's home directory is limited to 200 gigabytes. And this is really only for small files, scripts, and logs. And then the Scratch 3 folder that you have is designated for processing, and it's for short-term use only. So think of it as like scratch paper, doing some processing and then discarding what you don't need or the note afterwards. So you can place data here while processing and have outputs written here, but this space should be kept relatively clear when you're completed your job. You should review the data there, remove any intermediate files, and copy any data that you want to keep for a longer period to longer term storage in your project directory or your workspace, and delete everything that you don't need to keep. And note that in the last number of months, we've also implemented a 90-day Scratch auto deletion policy on our Scratch storage. So how this works is that we scan files on Scratch 3 mount and alert affected users of any files that are older than 90 days and specify that these will be removed on a specific date. So email alerts get sent out to users on the second and third Tuesday of the month, and the deletion of all the files that are older than 90 days happens on the fourth Tuesday of the month. There's more information about this in our user documentation if you want more details. And then the remaining storage or directory structure is split into different groups. So generally, as a user, you'll belong to an IDEA, cbio, and ilifu group. And we've partitioned the storage onto different mounts associated with those groups. So looking at the IDEA directory structure, if you're under the IDEA user group, as an example, a user in the IDEA group will have a folder at /idea/users. A user will generally always belong to a project and have access to a project directory, which will be located at /idea/projects. So for example, /idea/projects /mighty or fornex, etc. And then there may be other folders that contain data, raw data, or other software on the /idea mount. Your folder at your /idea/users is your private workspace directory where you can store data that you perhaps don't yet want to share within the project folder. So perhaps this is test data that you're working on or work related to a thesis, or you can place virtual environments in your workspace. And this directory is limited to 10 terabytes. The project folder is generally for sharing data and project resources within a project group. So key project activities and output should be stored here. And for astronomy projects, raw data associated with the project is also accessible from the project directory. Raw data for astronomy is generally read-only to prevent modification or deletion. And then there's also the software folder, which is the location of software containers and other IDEA-related software, such as the IDEA pipeline process meerkat. So there's a very similar structure for cbio users and ilifu users, with the exception that the ilifu projects are separated further into astronomy and bioinformatics projects. And for cbio, the databases are not linked from the project directories, but are managed by the cbio team. I believe they're in a database folder on the cbio mount. So just in terms of the typical workflow or how these directories kind of relate to each other, we've put together this diagram to kind of describe the recommended workflow on ilifu, with respect to the directory structures. So long-term data will generally be kept in a project directory or user workspace, or in a directory specifically to storing read-only data. When processing data on ilifu, you'll generally read the data from one of the folders on the left. So this will be the projects folder, or your /idea/users folder, or /cbio/users folder. And then you'll output your processing or write your results to your Scratch folder. And then once the processing is complete, you would then selectively copy the files or data that you want to keep from Scratch back to longer term storage in your personal workspace or the project directory, and clear any Scratch space, removing all intermediate products or files that you don't want to keep. So note that different projects and users will have different processing or data requirements. Some people are doing data reduction for meerkat observations, while some people are MS students, doing machine learning or image classification for an MSc project. So maybe your project doesn't generate a massive amount of data as part of some reduction process. If so, then perhaps you don't need to use Scratch. Perhaps you're an MSc student and you're just generating cutouts of galaxies to input into a machine learning algorithm, and the footprint of your data isn't very large. Then work in process within your workspace directory. You don't necessarily need to use Scratch. Generally, Scratch has two purposes. It's often high performance storage, such as SSDs that allow for high performance processing in comparison to other storage that is provided for longer term storage. Or it's used when Scratch storage is used when computation requires large amount of temporary storage. So you have like a large inflation of your data, but only while processing. And once you finish processing, the temporary or intermediate products can be quickly removed after some quality assessment. So make use of these resources depending on your requirements. And if you have any questions about the best usage, do contact us through the support channels for help. So I'm going to move on to software environments. We have three main environments we use on the cluster. Singularity, containers, software modules, and virtual environments. I'm going to focus on containers and modules today, and then we'll touch on virtual environments in the next workshop session next Tuesday. So containers, excuse me, containers are fully encapsulated software environments, which you can think of like all the application bundled into a single image, or like in a sense a compressed file. Except containers, they don't only contain the application files, but they also contain everything that you need to run the application, such as binaries, libraries, an operating system, environment variables, and they're all bundled into a single file, usually called an image file. And the benefit of containers are that they're easily portable. You can copy them from ilifu to other facilities. You can share them amongst project members or larger work groups. Some of you may have used Docker before, so Singularity containers are very similar to Docker containers, but the difference is that they're safe for use in an HPC environment because they don't elevate your privileges inside the container. So this diagram just shows how Singularity containers sit on top of the general system. So the container is the little box on the right of the diagram in the dashed box. And it may contain one or multiple applications. And the useful part of this illustration is just showing that with Singularity installed on the system, containers are run by using the Singularity launcher. So it's the Singularity binary. And the container environment can interact with the file system that exists outside of the container. So for example, when processing your data with an application in a container, the container environment and the application will have access to the directory structures that you have access to outside of the container. So for example, if your scripts are sitting in your home directory and your data is sitting in your project directory, the application in the container does have access to these. So you don't have to store your data inside the container is what I'm getting at. And the other benefit of containers is that they're able to be built with legacy operating system. You can put different operating systems, so it allows a lot of flexibility. For example, if you have some application that relies on legacy software. So we support a variety of containers. The list here is mostly astronomy containers. For example, Casa software used for radio astronomy reduction to produce radio images. But there are also bioinformatics containers and general Python or R containers for RStudio. We do offer to help you build containers with the software that you need for your workflow. So please do contact us in this regard. But you're also welcome to build your own containers. We don't provide information on building containers, but there are a lot of resources online on how to easily create Singularity containers. But we're happy to help in this regard. And then in terms of making use of Singularity containers, there's a number of ways, but the main two would be to use the container interactively. So you're interacting directly with the software inside the container on the command line. So this is done with the shell command. You would do this by running Singularity shell and then the path to the container. And this will place you in a shell environment inside the container, and you have access to all the environment variables and software, and it allows you to interact with it directly. And this is useful for debugging specifically. Alternatively, and this is how you would use the container when submitting a job on the cluster, you can execute a script using the software inside a container without having to shell into the container. For example, you can use Singularity exec and then the path to the container. You specify the software that you want to use and whatever script or input parameters. Hi, Sonchon. Is it possible to ask the question in the chat, or if you could keep it for the Q&A at the end, and then we can address any questions. But if you want to put a reminder, you can post in the chat. We're going to have a question and answer session at the end of the presentation.
Thanks.
Cool. So just as an example here, I'm running Singularity exec, and I'm using the casa6 container. Sm image is just Singularity image, and then I'm going to use the Python software and pass in myscript.py. So this will run my script using the Python that exists inside the Singularity, the casa Singularity container. And Dane, I think, will provide an example of this detailed in a job submission later in his section. So in addition to Singularity containers, we also provide modules. These are software packages that you can load into your environment. For example, when submitting a job, most of the modules are common programming languages such as Python, R, and Julia. There's a large number of bioinformatics software packages installed as modules rather than containers. And then some modules are actually just shorthand or shortcuts for calling containers under the hood, such as the Casa modules or the RStudio modules. So they're just, some of them are installed packages and some of them are just shorthand for containers. When you list the modules, they're divided into categories. So there'll be common modules. There's modules specific to astronomy and bioinformatics domains. You can view what modules are available by running the command shown at the top of this slide, which is module avail. And then just for information, the capital D in brackets just indicates which module would be loaded by default if you don't specify the version number. So you can see there's a number of kind of repeated software with different version numbers. And if you don't specify the version numbers, it generally will load the latest of that software version. So you can look at the help information associated with the module using the module help and then specifying the name of the module. So if a software has specific ways to be used or aliases associated with the software, these are generally detailed in the help function of the module or the help information of the module. You can load a module using the module load and then specify the module name. You can also module add does the same thing. And then you can run module list, will show all the currently loaded modules in your environment. Module purge will remove all the modules in your environment. And there's maybe a bunch of other commands to use with modules, and you can view the manual, the documentation, just using module -- help. So I'm going to go through a quick demo of modules and Singularity containers quickly. So just as a demonstration of what we've been talking about. So I'm going to first log into SSH into the Slurm login node. And I'm just going to run module avail. So this will list all the modules that we currently have installed. I think I press spacebar and there's a large number of modules. I think the list will end there. So you can see they're broken up into these are common modules, these are bioinformatics modules, and a smaller amount of astronomy modules. So just as an example, well, let me do module help CASA. And here you can see the help information or different tools you can use, for example, CASA Pi to launch CASA. So I think a number of modules have a help function, but if there's no special features, it might not provide a lot of detail. And then just as an example to show how modules work in terms of changing the software environments, if I go which Python from the command line, it's showing where my system Python is. And if I can do Python version here, it'll show 3.10.12. And then if I go module load Python, say 3.8.3, maybe a software that I want to use specifically uses or requires a legacy version. And I now do which Python, you can see that the path for Python has now been updated to use the module instead. And if I do Python version, you can see that the version has changed. So you can see how modules can be loaded to impact your software environment. So if I do module list, you can see Singularity is loaded by default, and then Python. I'll do a module purge, and now nothing is loaded. So I want to demonstrate the use of Singularity quickly. So I'm going to demonstrate shelling into a container as
You're
well
on the
as...
login node, Jeremy.
Oh, yes, I want to demonstrate that you can't run Singularity on the login node. So if you try to run Singularity, shell, etc., it will throw an error. So we don't want people to run software on the login node because this login node is small, but Dan will talk about the use case there. So what I'm going to do is I'm going to just jump to the develop partition using the sinteractive command, and now I can run Singularity. So I'm going to do Singularity. I'm going to shell into a container as an example. So this is a container that has a large number of Python astronomy packages included in it. So here I'm doing Singularity shell and then the path to the container, which is called AstroPy 3.10. And now I'm inside the container. You can see that the prefix of the command line has changed, and I can now access software that might not have been available before. For example, Python Cigale or Sophia, which is a source detection software. So I can now run these inside this container interactively. And if I can also, for example, I could load up Python, but I'm just going to pass in a print command as an example, to just show the interactivity. So here I'm using Python to print hello world inside the container. So this is an example of shelling into the container. As an alternative, I can execute a script using software in the container. So it doesn't open an interactive environment, but this is how you would say add this to a job script when submitting a job to Slurm. So here I'm passing in Singularity exec in the same container. I'm going to use Python, and I'm just passing in the same hello world command, and you can see the output. So that's just an example of using modules in Singularity. Okay. I got 10 minutes left. So finally, I'm going to speak about JupyterHub. So this is a web interface that you can use to spin up a Jupyter session that you can use for development or visualization. This is the login page and requires the username and password associated with your ilifu account. You don't require SSH keys to access any of the web-based servers. It just requires your username and password. And you also are able to now link your institutional account to your ilifu account using the edugain / Sapphire button. So here you can, if you belong to the University of the Western Cape or the University of Cape Town, you could link your institutional account to your ilifu account, and then you can log in using your institutional account. So once you've logged in, it will take you to the application dashboard. So I showed this before, but you can access a number of different applications here. And we're going to demonstrate Jupyter. Yeah, from here you select Jupyter, and you'll be taken to the JupyterHub launch page. So from here you can select a session size, and you can see what session sizes are also available to use. We have two different flavors of sessions now: a shared resource session type, where the CPU resource allocated to you is shared amongst other users of the same session type. And then we also have dedicated resources where you can select a session size, and you know that those resources are allocated to your user and not shared. We recommend in the first case to always use the development session where the resources are shared. And then if you need dedicated or larger resources for your task, then go and select a dedicated or large session size. A larger session size is generally only required if you need more RAM for memory intensive purposes, because CPU usage in Jupyter is usually quite small because of the nature of the cell execution. But because resources are shared amongst the community, please don't always go in and take the biggest possible available resource. Really select resources based on your requirements. And often the shared development session would meet most development requirements. So then after selecting your session size, you'll be taken to the launcher page in Jupyter Lab. And here you can select the kernel that you want to develop with. So these kernels can be used in the Jupyter Notebook or in a console environment. And then from the launcher, you can also actually open a terminal session, which provides a command line interface on the compute node where the Jupyter session is running. So I'm going to demonstrate this. So if you go to gateway.idea.ac.za, this is the landing page for the IDEA gateway, and you can select the application dashboard and log in with your credentials. So this will take you to the application dashboard. Here, please make note of the SSH key management to manage your SSH keys if you need to. But otherwise, for this example, I'm just going to use Jupyter. And you'll notice that I don't have to log in again to use Jupyter. It'll take me directly to the Jupyter service because I've already logged into the application dashboard. So here you can see what session sizes are available, and from the drop-down menu, you can choose different sizes. The development session is 2 core and 3 gigs of RAM, and it's shared, while the other ones, they kind of double in resources as they increase in size. And there's also GPU resources available. So as good practice, I'm going to select the development session first, and this will take me to the lab launcher. So I've already got a notebook open from a previous session, but actually what I want to do is just show you the landing page, which you'll generally see first, which
5 minutes, Jeremy.
Okay, thanks, Dane. So this is the launcher page, and you can see the different kernels here. So you can choose which kernel you want to develop with. You can also create your own custom kernels, which through a Python virtual environment, but I'm gonna go into that detail in the session next week, Tuesday. So just as an example, I'm going to select the latest Python 3 AstroPy container. So this has a lot of astronomy packages developed in it. And here I have cell execution. I can start developing. If you want to change the kernel, you can click on the kernel in the top right-hand corner here, and you can select an alternative kernel from the original list. But I've actually got a pre-generated notebook. So this notebook is in the in the GitHub repo for the tutorials, and I just wanted to go through some of this in a bit of detail. So as I mentioned, you have the launcher page or the notebook panel on the right-hand side, and then you have on the left-hand panel is your directory navigation, so you can navigate from your home directory to your workspace and navigate the directory on ilifu storage from here. Jupyter works with cell execution, so you can run or you enter code and run command or cell at a time. So here you can see just a very basic Python code, and the numbers on the left-hand side of each of the cells as they're being executed just indicate the order in which they're being executed. So very basic information. Jupyter allows mouse navigation. There's a shortcut bar at the top here, which allows you to execute shells or stop code from running. And it also allows keyboard navigation. So if you use Vim, you might be familiar with some of these. You can create a cell or above or below your current cell using A and B, or you can use DD to delete the current cell. So these are really useful, makes coding quite quick, or speeds up your use of the platform. Other useful tools are from the menus at the top here. So here you can run different cells or run all of the cells below the current cells, for example. And for kernels, you can restart this kernel, clear any outputs, or reset all your variables from this interface, or from this menu, sorry. I'm going to skip over some of the detail. So it does allow tab completions of function names, which is very useful. You can also do shift tab with a function next to the function that you're looking at to look at the doc string of the function. So it's a very useful development environment. Similarly, you can prepend a question mark at the end of the function if you need to know what the inputs are. For example, it'll print out the doc string. You can also upload files to the current folder using this upload button, although it works for small files, but we found that it's not very good for large files. It does cause corruption. So if you want to upload large files, it's better to use other transfer features. And then you can also execute commands using or prepending exclamation mark. And this will execute commands from the cells in the underlying Linux environment. So for example, here I'm just listing my current working directory or making a new folder, for example. And then as I mentioned, you can also open a terminal window in Jupyter too. What's great is that you can write Markdown as well as code. So all this information above here is actually written in Markdown. So if I show you the actual code, here you can see the Markdown. And then when it's run as a cell, it just converts it to Markdown format. So it's really useful to create tutorial or information, or you can populate your coding notebooks with information to explain what you're doing, or output images and visualizations. So here's just an example of running using NumPy and matplotlib to just plot a basic sine wave. So here I'm executing the cells, and you can use it to debug variables, etc. Dane's gonna give me the evil eye if I don't finish up soon. And I'm gonna rush ahead and just mention the most important thing is stopping your Jupyter session. So if I had to just close the notebooks and close my session, that doesn't actually stop the session that's running, because you can step away from your laptop and come back and reconnect to the same session that is currently running. So what's important, if you want to release the resources so that other people have access to the resources because you're not doing development, what you need to do is you go File and then Hub Control Panel, and you click Stop My Server. This is also a way if you've chosen too small a session, you want to go a larger session, you can then go Start My Server, and it takes you back to the launch page. and you can choose a different session size. But it's really important to release your resources if you're not going to be using them for a while, especially for larger session sizes, like large half max or max sessions, where you're allocating a very significant chunk of resources to yourself. So please do take that into consideration. And I will stop there and hand over to Dane for introduction to Slurm. You're muted at the moment, Dane. Okay, cool.
And now?
Yeah, I can hear you fine. And I
All
can see your
right, let me
slides.
just try and move these out the way. There we go. Yeah, hi, good morning, everybody. Thanks for that, Jeremy. Yeah, my name's Dane. As Jeremy said, I'm employed at ilifu as a bioinformatics support contact. So I do a lot of that, and then I also help out a little bit with kind of Slurm administration and some other things like our users portal and help desk. But yeah, this presentation is about Slurm, what it is, how to use it, as well as some pro tips and best practices. You won't be an expert by any means by the end of this, but hopefully you'll be more familiar with some of the concepts that you will use on the cluster, and with any luck, more comfortable asking us questions, which you can do at any time. I think Jeremy already told you about the different ways to do that. So what is Slurm? Slurm is an open source workload manager or scheduler. What it does is it allows you to submit computing tasks or jobs, those terms are interchangeable. You can submit those jobs to a computing cluster. Jeremy told you a computing cluster is a collection of computers or servers, normally connected with some nice storage and a nice fast network. But the workload manager figures out when and where computing jobs can be run, and it keeps a record of their resource usage for accounting purposes. From a user's perspective, that's you, there are three main components that you should be aware of. Firstly, there's the login node, which, apart from Jupyter, this is usually your first point of contact with a cluster and the place where you will do most of your interactions. It's not a server to use for big computing tasks, but rather it's a place for administrative tasks such as submitting jobs, editing scripts, and light management of data. The login node is a shared resource, so you're sharing it with all the other users at the same time. So any misuse impacts others negatively. So we monitor it closely and are quite strict about how it's used. Accidents do happen. So if you accidentally do something you shouldn't be doing on, we might kill it and send you a gentle reminder. But yeah, it's not the end of the world, but please don't do it. And then secondly, we have compute nodes. These are bigger servers and the place where computing jobs are run. Once you're running something on a node, the resources you've requested are allocated to you. This means that nobody else can interfere with the running of your software. But the other side of that is that you should be as accurate as possible when specifying those resources. This is covered in more detail in session 2 by Tinnis, I think. And then finally, there's Slurm itself, which has three key functions. Slurm allocates access to resources for users. In other words, sorry, my notes. This is reserving memory and CPU resources on the compute nodes for your jobs. Slurm provides a framework for starting, executing, and monitoring your jobs. And I'll show you some of these commands a bit later. And then finally, it manages a queue for pending work. So when you submit a job, it first sits in a queue and waits for its turn to run. In Slurm, these queues are called partitions. If you use something like CHPC, I think they're called queues there, but it's the same thing, queues and partitions. And we have several different partitions that you can choose from, and I'll cover that a little bit now. So there are various ways that we might want to group the nodes, but this graphic shows them grouped together by primary function, and the table groups them by their partitions. So if we look at the first image, there are 4 groupings. There's the login node. As mentioned earlier, this is where you perform basic administrative tasks, such as running bash and slurm commands. Then there's the Jupyter development partition. Think of this as a development space for testing new software, plotting results, building workflows, debugging, or demonstrating things like Jeremy did earlier. Then there's the main partition. So this is where most stable and computationally intensive jobs are executed. By stable, I mean the code isn't changing. It's an established process that only differs in input and output. Parallelism is possible, or jobs may be split into smaller tasks. And finally, we've got the high mem or GPU partition. We don't really cover this in detail in this presentation, but the high mem partition is designed for single high memory jobs that can't be split up. And the GPU is obviously for GPU-based jobs. A little bit more information about the nodes in this table. So the nodes in the main Jupyter development partition mostly have 32 cores and about 230 gigs of RAM available. This varies a little bit. So we've got some 48 core machines in there as well, and some have a bit more memory available. But it's roughly what it is. And we've got something like 95 of those. I don't know if these numbers are quite accurate right now. And we've got 8 GPU nodes. These again are similar to the main partition, except they have GPUs, and we've got a range of different GPUs, and some nodes have 1, some have 2 GPUs, so it depends on which node you're on. And the high mem, we've now got 8 of these. Most of them are these 32 core 500 gigabytes of RAM variety, and then we've got one beast which has got a lot more cores and quite a lot more memory. Then that's pretty much all I wanted to say about that. This slide, yeah, it just very quickly depicts the 2 main ways you may interact with a cluster. So you've got Jupyter, which Jeremy showed you earlier. And then on the right here, we've got what I'll be demonstrating later, which is our interacting more directly with the Slurm cluster on a terminal, shell terminal. Yeah. Sorry, the one thing I wanted to say about Jupyter was that when you're running a Jupyter job, like Jeremy showed you earlier, what it actually does is submit a job on the Slurm cluster. So all those Jupyter lab interactions you have are actually running on a compute node in the Slurm cluster. Okay. So let's talk a little bit about the terminal and the commands you might be using. And first of all, what you need to do is connect to the cluster, and you'll be using the SSH command to do that. Once you've landed on the node, here are a bunch of the basic Slurm commands you might want to use. The sinfo command shows you all the partitions and resources that are available. squeue shows you all the jobs that are sitting, waiting to run or are busy running. Sbatch is the command you will mostly be using to submit jobs. And finally, scancel is to cancel a job that's maybe sitting waiting to run or is running and you've realized something is wrong. I'll demonstrate all of these in a moment, except for scancel. So when you submit a job, you need to have a job script. And what is a job script? It's a simple bash script that describes what resources your job requires and then the steps your job should do in order to process your data. This that I got here is almost the most simple job script you could have. The very first thing is this shebang line. This is called a shebang. I don't know why. Hashbang, shebang. But basically what this is doing is telling the interpreter that you need to use bash to run this. Bash is just a shell. It interprets the lines. Then the next lines we've got here are the commands that will be run. In this case, we're going to use the module system, which Jeremy also showed you. And what we're doing here is we're selecting Python 3.11.2, and then we're going to run the Python command on this hello world script. And that's all there is to it. And I'll demonstrate this in a moment. But Slurm is in charge of allocating resources. And the question you might be asking is, how does it know which queue to run on? How many CPUs will it use? How much memory? How long will it run? Well, the answer is there are a bunch of defaults that we haven't specified here. And by default, this is what they will be using. So if you don't specify anything, by default, we'll be running a job for about 3 hours. And if you go over that, your job will be killed. It will use 3 GB of RAM. It says there's one task run on one node, which basically means it'll use one CPU on one node. It'll run in the main partitions. We told you about all the queues earlier. It'll run on the main partition. And you've got when you get your account, you normally get a default. You might be a member of multiple projects, but you will have a default set up. We can show you a bit about that later. When you log in, it actually tells you what your accounts are and what your default is. And I'll point that out to you. So if we wanted a more complicated script, we might have one that where we explicitly set some of those parameters. So here we've got a bash script, hashbang bin bash. But the difference here is now we've got these parameters set. The first one we've got here is a job name. I recommend setting something quite descriptive here about your job. Otherwise, it defaults to the name of your script file or bash or something like that. So I think it's very useful when you're looking at past jobs to have explicitly set a meaningful name here. And for this job, we specified a wall time of 1 minute. So this is the maximum time that your job will run. This format is days, hours, minutes, seconds. So this is 1 minute. I specified that my job needs 4 GB of RAM. So that 4 GB of RAM gets set aside. Nobody else running on the node, which you can have multiple people running on the same node, but you will have 4 GB of RAM set aside for you. It's going to run on the main partition. These two parameters are pretty useful. So these specify your standard output and your standard error. So if you're familiar with Linux, Unix, whatever, there are 2 streams that programs can communicate with you, and there's a standard output, which is where most of the output gets written, but there's also a standard error. It might not be obvious, but yeah, you can separate them out. And explicitly setting these file names is useful because it lets you easily see where the expected output is, and if anything went wrong, it'll normally populate this file. This %j is actually something that Slurm will interpret, and it just says substitute in the job ID. So when you submit a job, you get a unique ID, which is just a number, and it'll get substituted in here. Then you can also get email notifications about how your job is going. There are various different types: when your job starts or when it ends, if something goes wrong, or if you're approaching the end of the wall time that you specified over here. You get notified for those. You do need to remember to fill in your email address, which you do here. And finally, explicitly setting your accounting group in case you're a member of more than one project. So once you've done that, you tell it what commands you're going to be running. And in this case, we're running this Singularity container with some little R script. Yeah. How are we for time? Fine. So this is the table with some of the defaults and maximums for the different partitions you might use. So here we can see the three main partitions, which are main, high mem, and GPU. Within those, you've got a little bit of variation. So here we've got these nodes have a few more cores. These nodes have a little bit more memory. They all default to having a maximum. They all default to 3 hours, but these all have a maximum of 14 days wall time. And this development node, I'm actually not sure this is right anymore, but it's the development node we have a shorter wall time on. That's the shared resource. Yeah, they all default to one CPU, and like I said, they got different. The high memory default to slightly more memory in your job. Yeah. I think that's all I wanted to say about this. So, oh, is it demo time already? Okay. Please feel free to interrupt me at any time during this, because this is basically the last thing I talk about during my presentation. I need to check this link, but we'll let you know it's close to this. Yeah, no, this is correct. This is the correct link. So the tutorial is available there. Let me get to my shell. Oh, don't want to go there. So hopefully you all have some kind of terminal, whether that's just in your Linux or Windows subsystem for Linux or PuTTY or yeah. But basically, once you've got your account, you're going to be able to run the SSH command. So the first thing we're going to do is this SSH with my username to the cluster. And once we do that, it connects. And the first thing you'll see is this great big welcoming message. I do encourage you to please read through this at least once every week until you know it all off by heart, because there's some important basics that you need to remember. But like I said, when you SSH, you do get this little message. It tells you what your accounts are. So my default is this admin account, which none of you will be on. You'll have something more like this. But it does highlight your default, and that if you don't specify your account, any jobs you submit will go against that. Also, it tells me I'm not running any jobs at the moment, and then I'm waiting to run. So the first thing I'm actually going to do is just change to this directory. So there's the cd command, which is change directory, and I set this up earlier with a tutorial. And if I clear the screen, and ls is the command you use to list the contents, I can see I've got a handful of files, this readme, hello world, and these two batch scripts, which we're going to be working through in a moment. Other commands I wanted to show you are sinfo. This is a command that shows you the state of the partitions. So we've got our main partition nodes, some are down. These are actually being used for another course that's being run. We've got 19 nodes in this mixed state. So these are jobs that have these are nodes that have some jobs running on them, but they still have resources available. So they can run more. And then we've got 57 nodes that are fully allocated. So there's no more space on any of them to run any jobs. And we can see similar for the GPU nodes. Sorry, just Jupyter nodes, but the GPU nodes, we've got 4 idle GPU nodes. So if somebody needed a full node, and if they needed a GPU job, they could run on a GPU node. And then finally, we've got our development node, which we'll be using today. And it's mixed. So the development node is special in that you can over allocate. So you can have more than 32 small jobs running on there. So I think it's, yeah, but so those are shared resources. You have to use responsibility. You don't want to use all the memory because it'll impact others. So remember, it's for development and small testing purposes. Then we've got the squeue command. This is the command that shows all the jobs that are either running or waiting to run. I'm just going to do this so we don't get too much. Let's do even less. So here we can see jobs that are running. It tells you the job ID, tells you which partition that job is running. Here are these meaningless names. So that's why I recommend setting a name like these guys. Maybe this must mean something to these people. It tells you the state. R means running. PD means pending. So this one isn't running yet, and it tells you there aren't resources available for that GPU. So they must need a GPU that's busy. And yeah, it tells you if your job is running, it tells you which node it's running on. All these commands have built-in help. So if you run -- help, it'll show you more. And it tells you all the different options you can use. So you could say you want to see all the jobs that are running against a specific account or specific partition, say. So that's good to know. So we've covered sinfo, squeue, and now we can go into sbatch. So sbatch is the command that we use to submit a job to the scheduler. Again, it's got a help, but we're going to be using it in a very simple way where we specify all our parameters actually in our batch job, which takes me to this minimal script. So this is the smallest job script we could have. So I told you about the hash bang earlier. I've added in, I'm specifying a partition, which you don't have to do, but I'm doing it just to guarantee that my job runs. And all it's doing is running this echo hello world command. So I can show you what that does. I'm sure you can guess. That just puts hello world on the screen. So we're going to run sbatch with this minimal script. And what we get is, it tells us we submitted a job and we got a job ID. I didn't cover earlier is this X control, but I can say S control show job and I can give it a job ID. And it shows me the state of the job, which is completed. But I do want to just show you a couple of other little things, like the default. It set the default time limit as 3 minutes. It set the job. So I always find this a little bit difficult to read, but set our Trez, our resources. So Trez is trackable resources, but it says we need 1 CPU. Because it's on Devel, it allocated 232 gigs of RAM, which isn't actually what it, on the main partition, that'll be limited to 3 normally. And it's on 1 node. Somewhere here, it will say it ran against that default account I told you about. And then somewhere here it says partition. I can't see it right now, but it's there somewhere, but it'll say Devel. Yeah, partition says somewhere here. There we go, develop. There it specifies devel. So it set a whole bunch of defaults. And now what we're going to do is we're going to slowly add parameters and we're going to check what changed. So I'm going to edit this minimal script. And first thing I'm going to do is give it a decent job name. I'm just going to be copying and pasting because we have limited time. What did I copy? Sorry. I could have typed that quicker. Hey, demo time. Oh, the other thing I should have showed you is that it would have created this default little output file. And if we look at the contents of that, it put our hello world text there. Why is that little icon there? I don't know. So that's how it updated it, output to the screen, and it created this file Slurm with this job ID, which is the same as our job ID that we got when we submitted it. Okay, but then now we've updated our script to have a different name. Let's actually add a bit more because we have limited time. Okay, so we've specified a job name, but I also want to add, let's say, a wall time and a memory. So now we should get more sensible values for those. We're going to submit it.
Then you can't specify memory for the develop partition.
Can you not?
I don't think so.
That'll teach me not to check that. Okay, we're going to leave that free for Devel. Okay, we've got a new job ID. We're going to use that. And it should. Again, it's completed, but now we should see our time limit was increased to a minute, or decreased to a minute from 3 hours, I think. And we've got a decent job name. But the rest should be the same. If we look at 754, anyway, it did the same. It again produced this hello world. And that's all we added. So let's add a bit more. So we're going to add, I want to change our standard output and our standard error files. Let's do it manually. So we're going to do sbatch output equals, hi everyone. We're going to put in %j dot standard out. And we're going to do an error file as well. Error, okay. I think that's fine, but then let's change it a bit. We're going to use a module, Python dash, doesn't matter too much which Python we use. And we're going to run this command. Hello world .py. We can just comment this out. Let me just quickly show you what the hello world script looks like. It's very simple. Essentially, what it's doing is in the main function, it just outputs a whole lot of information about the running job, where it's running, and some environmental variables are set. But it also writes something to the standard error file just so we can demonstrate what's going on there. So it's very simple, not much more complicated than echo hello world. And we're going to submit it again. Woohoo! Typo unmatched. Don't know how I put those in. That should be fine. Okay, should run very quickly. Pending. That tells me I've probably got a bug in it. Maybe it's just slow. Completed. Phew, I don't know why it took so long. Probably because I was using Python and Python was a bit slow to load up, which can happen. So mostly what we've got is the same, except now we'll see we've got, it's a new standard error file. So that file should now exist. We'll check in a moment. And we've got the standard output. Let's see, do they exist? They do. Oh, did I put %k? I should have put another typo. Should have been %j. But we've got the file anyway. So if we look at the contents of this, our standard output file, we will see now its output what we expect. So it's hello Dane. It was running on compute 001, which is our development node. And we can see that a whole bunch of environmental variables were set. And this is their contents, which mostly isn't information that we need right now. And we can check the standard error file, and that should have that error message I told you about. And there it is. Yeah, then we can look at our one more example, which is pretty similar to what we had. I've called it maximal. The only difference here basically is instead of that Python script, we're going to be running an R script, which outputs something similar, but we're using Singularity. So this is just demonstrating how you might use Singularity. Oh, let me just quickly change this as well. So it should be Dane at. So now it's also going to send me an email to my email
You might
address
have
when
to remove the memory, Dane, sorry, as well.
Thank you. Yeah, so it's going to send me an email when the job starts and when it ends, because it shouldn't fail and it shouldn't reach the time limit. So maximal submitted. Let's check if squeue. It ran too quickly, but we check the job. We can see it completed. There were no bugs in it. If there are bugs, you might get a job status fail as well. We can check the contents of this standard error file. I think it's empty, good. And then our standard output is similar to our Python example, just formatted a bit differently. Yeah, I think that's pretty much everything I wanted to demonstrate to you. Just quickly check my notes. Haven't forgot anything. Yeah, that's it. Back to the slides. I just want to highlight again a few of the do's and don'ts. So remember to use sbatch for running jobs rather than accidentally just running your commands straight on our login node. It's important to accurately describe your resources for your jobs, number of nodes and CPUs, as well as the RAM and wall time that you need. If you underspecify wall time, your job will get killed before it's done. And if you overspecify, it's not too bad, but it does sometimes mean your jobs will be slower to start because the Slurm scheduler uses something called, I've forgotten the word, but if it backfilling, yes. So if it sees some other jobs are scheduled to run already, but they're only going to be starting in an hour because there aren't resources available. If you've got a small 50-minute job that can run in that time, it'll quickly slot it in, even though the other guy might have higher priority over you. So there are lots of reasons to specify your resources accurately. Always remember to remove files that aren't needed. So scratch3 is for temporary data generally, and we really helps us a lot if you can remove that data as quickly as possible. So that, because it's a shared, as with everything on ilifu, Slurm, it's a shared resource, so you need to be considerate of others. You're going to battle to install your own software on the cluster. So you can use Singularity containers, which we can build for you, or you can use ones that are already there. And then we've got this transfer node that we want you to use for data transfers. So if you're copying data to or from the cluster, use this transfer node rather than the login node. This is covered in more detail in one of the later sessions. Yeah, don't run stuff on the login node, but don't put large files in your home directory. Use your project space rather. Yeah, I think that's it. Thanks very much for your time. Please contact us on support and read the documentation.
Thanks, Dane.
That's it.
Thanks for the presentation. We'll open for Q&A now. So if anybody has any questions, you're welcome to ask. But I am going to start with the questions that have been asked in the chat already, because I think it's useful to speak to the questions and for everyone to hear the answers, really. Shunchuan asked, by default, Singularity will be executed on which node? And Dane did respond. And so he said, running Singularity will run on whichever node you're on. To run on a different node, which you must do, you'll submit either an interactive job or a batch job, which he did demonstrate. So I guess, yeah, just to avoid any confusion, when I was demonstrating Singularity, when I tried to run it on the login node, it came up with an error message saying, stop, you're trying to run this on the login node. You need to submit it as a job or use the develop partition. So that's just to clarify that we don't want users to run anything on the login node because this node is small and it can impact the performance of that node for other users. So always run software as a job, or even using the develop partition is technically a job. You're assigning resources for yourself on the develop partition. You can run software there too. Yeah, Shanjuan, if you have any other follow-up questions, or if you need more clarification, let me know. And then Surprise asked if I request an interactive job on Slurm and the job is detached for some reason. So if you get disconnected from your terminal session, does it mean that the same interactive job is terminated? And yes. So if you run, we're going to cover interactive jobs. So Dane covered sbatch or submitting batch jobs on Slurm today, because that's our preferred way of running jobs on Slurm. But you can run interactive jobs using, we have the S interactive command, which I demonstrated in my demo. But you also have an srun command, which Tinas will demonstrate or talk about in more detail in the session next week. We don't have time to cover everything. But if you are running jobs interactively, if you get disconnected, your network drops, and you're no longer connected to your interactive job, it does mean that it will die. And so Tinas will talk about this next week, but we recommend using, and Dane responded as an answer, to use persistent terminals. So that's a software, for example, Screen or Tmux. If you run Tmux on the login node, for example, and then start an interactive job, if you get disconnected, you can always then SSH back to the Slurm login node, reconnect to your Tmux session, and then your interactive job will still be running. So that's a way to kind of overcome that issue of the detaching from interactive jobs. I think I covered. Yeah. And Shuntron asked about what is standard output of sbatch. So basically like the Linux information streams from running software. If software has any information output like logging or is printing out information to the terminal generally, when it's processing or running, that's called your standard out. And the other stream that Dane indicated was standard error, which is another stream which is defaulted to standard out in Slurm, but you can specify a separate file. So Dane just demonstrated that it's really useful to indicate where your software output or logging is going to be directed to a specific file, because once your job is complete, I mean, obviously you might have it outputting, some sort of other data format, but to go and review what your software ran, it's often very useful to go and review the standard out logging files that get created with each job. And if you hit an error, it's useful to review the standard error files. Can easily point out where things are going wrong when debugging issues. So those are the questions we've received so far. If you have any other questions, you're welcome to put them in the Zoom chat, or you're also welcome to unmute your mic and ask the questions directly. Thank you very much, Ntebe, for your feedback. And thanks everyone for joining us today. So we covered introduction to ilifu, we covered the directory structure and the software environments, including Singularity containers and modules. And then we also covered Jupyter and using Slurm with sbatch. So thanks everyone for joining us, and hopefully we'll see you next week, Tuesday. And thank you very much for the questions. It's really great to have the questions and engagement with everyone.